The aluminium extrusion process begins with the casting of aluminium alloy logs. This involves melting high-purity aluminium along with a combination of purchased and in-house scrap, and adding specific alloying elements, commonly magnesium, silicon, copper, or manganese, depending on the desired material properties. For example, the 6063 alloy is primarily composed of magnesium and silicon, which together form magnesium silicide, a compound that significantly enhances the strength of the final product. The molten aluminium is poured into a furnace where the alloying elements are introduced. This step is crucial, as it allows precise control over the chemical composition, ensuring the final alloy meets strength, machinability, and other performance specifications. To refine the metal and remove impurities, the molten aluminium is subjected to a degassing process using spinning rotors and then passed through a filtration system. These steps improve metal quality by removing gases and unwanted particles, and help refine the grain structure for better mechanical properties. Once purified, the molten aluminium flows into a casting unit, where it is cast into long cylindrical logs, typically 20 to 30 feet in length. With in-house casting facilities, companies like Sapa gain full control over the production process, ensuring consistent quality, a wider range of alloy options, and quicker turnaround times for customized orders. Following casting, the logs undergo homogenization, a high-temperature thermal process that enhances their microstructure and improves their extrudability. After cooling, the logs are cut into billets, which are smaller, more manageable pieces, typically ranging from 20 to 50 inches long. Before extrusion, billets are reheated to between 800 degrees Fahrenheit and 1000 degrees Fahrenheit for malleability. Both the billets and dies must be uniformly heated. Extruding a hot billet through a cold die could damage the die. Once heated, a ram pushes the billet through the die to produce the final extruded aluminium profile. Extrusion methods are crucial in shaping aluminium into precise profiles for various applications. Two main techniques are used: direct extrusion and indirect extrusion. In direct extrusion, the heated billet is pushed by a ram through a stationary die. This is the most common method, but it generates significant friction between the billet and container walls. The center of the billet flows faster than the outer edges due to this friction, creating challenges for dimensional accuracy and requiring more energy, sometimes up to half the total extrusion energy. Friction can also lead to variations in temperature, affecting the final product's properties. Indirect extrusion, in contrast, reduces friction significantly. Here, the die is mounted inside a hollow ram, and instead of pushing the billet through the die, the entire container and billet move together toward the stationary die. This method results in lower friction, more uniform temperatures, and consistent dimensions and grain structures. However, indirect extrusion is limited by the size and complexity of shapes it can produce, because the tooling must fit inside the hollow ram. Additionally, billets must be scalped to remove the outer layer before extrusion, ensuring surface quality. Heat treatment is a vital stage in the aluminium extrusion process, particularly after extrusion, to achieve the required mechanical properties. The first and most critical part of this process is quenching, where the hot extruded profile is rapidly cooled using air fans, water sprays, quench tanks, or a combination of methods. Quenching locks in the alloy's microstructure, preserving the phase and element distribution to meet strength requirements. However, rapid cooling can cause internal stresses leading to distortions such as twisting or bowing. To correct this, the extrusions are placed in a stretcher, which straightens the profile and relieves internal stress. For 6000 61T6511 temper, a typical stretch range is between 1 to 3% of the extrusion length. After stretching, the profiles are cut to specific lengths, either to final size or rough cuts for further processing. Dimensional accuracy is then verified using precision tools like calipers, micrometers, and straight edges to ensure they meet all tolerance requirements. Aging is the final heat treatment step in the aluminium extrusion process, used to achieve the desired mechanical properties such as strength and hardness. Once the extrusions pass dimensional and mechanical inspections, including tests like hardness, tensile, or bend testing, they are loaded into aging ovens. A typical aging cycle lasts 6 to 8 hours at elevated temperatures, depending on the required temper, e.g. T6. This controlled heat exposure allows the microstructure to stabilize and reach full hardness. After aging, extrusions may undergo final fabrication like CNC machining, punching, welding, painting, or anodizing before being packaged and shipped to customers. The process begins with the lifting carriage material magazine, which is responsible for the safe and automated handling of raw billets. This magazine system efficiently stacks and feeds billets into the production line, minimizing manual handling and reducing downtime. It prepares the materials in a controlled manner, ensuring smooth transitions and continuity in operation, especially critical for 3-shift industrial schedules. Once the billets are loaded, they pass through a scanner and length measuring device. This component precisely evaluates the size and position of each billet. By measuring and identifying individual billet lengths, the machine can optimize cutting cycles and minimize material waste. This feature enhances operational efficiency and ensures high-precision cuts in line with production specifications. Next, the billets are moved forward by a material feeding tong system. This mechanism securely grips and positions the billets for cutting. Its high level of control ensures consistent feed rates and accurate alignment of the material. Importantly, it works seamlessly with the unique 3-point clamping system to handle even bent or irregular billets, ensuring secure clamping and minimizing the risk of miscuts or vibration during sawing. At the core of the system is the KSS 1600 sawing machine itself. This robust circular saw is specially engineered to deliver high-performance, clean cuts in a range of billet materials. The inclined bed design merges the best characteristics of horizontal and vertical saws, allowing for space efficiency and enhanced chip removal. Its design also facilitates maximum stability and minimal deflection during cutting, thanks to its compatibility with high-end Lincut and brazed saw blades. The KSS 1600 is tailored for continuous operation, making it a reliable choice for round-the-clock production. After sawing, the cut billets are transferred via the outlet chute with a pusher device. This automated system efficiently moves finished pieces away from the cutting zone, maintaining workflow efficiency and preparing them for subsequent processing or transport. The pusher ensures that even heavier billets are handled without manual intervention. To complete the process, an integrated scrap removal system ensures that all offcuts and waste material are promptly and safely evacuated. This helps maintain a clean work area, minimizes the risk of jamming or mechanical faults, and supports environmentally responsible disposal or recycling practices. The aluminum billet production line includes a melting furnace for liquefying metal, degassing for purity, casting machines for shaping, and automatic cutting. Billet casting tables mold molten aluminum into solid billet forms. The molten aluminum flows from the melting furnace into the launder, a specially designed channel that guides and controls the metal's temperature and flow rate. The launder ensures a steady, uniform stream of molten aluminum enters the casting tables without turbulence or contamination. Inside the casting tables, molds shape the aluminum into billets as it gradually cools and solidifies. This controlled transfer process is crucial for producing billets with consistent dimensions, smooth surfaces, and high metallurgical quality for subsequent processing. The skimming process involves removing impurities, dross, and oxide layers that float on the surface of molten aluminum before casting. Using specialized tools or automated skimmers, operators carefully skim off this unwanted layer to prevent defects in the final billets. Effective skimming ensures cleaner molten metal, resulting in billets with better surface quality, mechanical properties, and reduced risk of internal flaws. Aluminum billet forming occurs as molten aluminum cools and solidifies inside molds on the casting table, creating long, cylindrical, or rectangular billets with uniform shape, smooth surfaces, and precise dimensions. A crane lifts and removes solidified aluminum billets from the casting table, safely transferring them for further processing like cutting or inspection. After removal from the casting table, The aluminum billets are carefully transported and positioned onto the automatic cutting machine. This machine uses precise saw blades to cut the long billets into specified lengths according to production requirements. Accurate sawing ensures uniform billet sizes, reduces material waste, and prepares the billets for downstream processes like extrusion, forging, or storage for future use. Production begins with aluminum billets, typically 16 inches in diameter, which are cut to required lengths using a dedicated billet cutting machine. Before extrusion, the billets undergo preheating in a die preheating furnace. This controlled heating ensures the aluminum reaches optimal plasticity for smooth flow through the extrusion die. At the heart of the operation is a powerful 6,000-ton seamless/seamed dual-purpose extrusion press, capable of producing profiles with cross-sectional diagonals up to 500 millimeters. During extrusion, the heated billet is forced through a custom-designed die, shaping the aluminum into continuous lengths of the desired profile. After extrusion, the hot profiles undergo quenching and are transferred to a 450-ton straightening machine. Next, profiles are subjected to artificial aging in a 13.5-meter heat treatment furnace. This heat treatment process improves mechanical properties such as strength and hardness, crucial for structural applications. Surface finishing is another critical step in producing large-scale aluminum extrusions. The facility includes an in-house anodizing department capable of handling profiles up to 6 meters long. Anodizing enhances corrosion resistance, surface hardness, and appearance. Additionally, profiles may receive liquid painting, powder coating, or fluorocarbon coating, each offering unique protective and aesthetic properties suitable for diverse environments and design requirements. Precision machining follows, using multi-axis forming and straightening machines. These machines ensure tight tolerances, accurate shapes, and consistent quality across all extruded sections. For further processing, cutting operations are performed on advanced saw tables. A double-cut 45-degree saw table allows fast, precise angle cuts, while a computer-controlled automatic saw table achieves accurate length cutting and smooth, burr-free edges. Large-scale aluminum extrusions are essential for applications ranging from architecture to transportation and industrial machinery. The manufacturing process integrates advanced equipment and precise engineering to ensure high-quality profiles with excellent mechanical and surface properties. Large-scale aluminum extrusions are essential for applications ranging from architecture to transportation and industrial machinery. The manufacturing process integrates advanced equipment and precise engineering to ensure high-quality profiles with excellent mechanical and surface properties. With its high rotation speed and a complete in-feed roller table system, Dejin Offshore in China is pleased to drive innovative production. The patented HAEUSLER system, equipped with upper and side supports, enables precise bending of diameters up to 15 meters and handles loads of up to 150 tons. Whether forming heavy wind turbine towers for onshore or offshore operations, or producing large monopile constructions, the VRM masters the demanding challenges of these industries like no other. Its pioneering technologies ensure exceptional efficiency, precision, and safety in handling massive components, setting new standards for modern manufacturing. Dejin Offshore benefits significantly from this advanced solution, further solidifying its position as a leader in the global energy and infrastructure sectors. The FKB Large Bending Plate Machine is an advanced solution for precision bending of sizable metal plates, delivering a powerful maximum force of 3,700 kilonewtons. Designed to handle plate widths ranging from 2,500 millimeters to 13,000 millimeters and thicknesses between 4 and 9 millimeters, it offers exceptional versatility for heavy-duty applications. A standout feature of the FKB is its innovative Bendtronic control software. Bendtronic streamlines the entire bending process, allowing operators to visualize, program, and adjust bending sequences with remarkable ease and precision. Even complex bending geometries can be managed intuitively, reducing setup times and increasing productivity. With a robust top roll diameter of 180 millimeters and a substantial machine weight of 165 tons, the FKB ensures stable, consistent bending results even under the highest loads. Despite its formidable capabilities, the machine is engineered for user-friendly operation and seamless integration into diverse manufacturing environments. Its overall dimensions of 18 by 4 by 8 meters reflect the machine's industrial scale, yet its adaptability is a key advantage. Originally developed for specific heavy industries, the FKB's outstanding accuracy, flexible configurations, and user-friendly control software have led to its successful adoption across a wide range of sectors, from shipbuilding and energy to architecture and specialized fabrication. The continuously cast billets are square blocks measuring 130 or 180 millimeters, weighing 1.3 to 3 tons, heated to approximately 1,150 degrees Celsius, lengths 11 to 900 millimeters, with dimensional tolerance plus or minus 3 millimeters. After heating, billets enter the rolling mill, where high-pressure water jets descale their surfaces, removing scale and impurities. They then pass through multiple rolling stands, each shaping and reducing the steel's cross-section to form precise bar profiles. Rotary shears crop bar ends for uniformity. To achieve required strength and toughness, the hot bars undergo rapid, controlled cooling in the temp core system. Subsequently, bars cool gradually on a cooling bed before being cut by shears into customer-specified lengths for final bundling and dispatch. First, iron ore is smelted in a blast furnace to produce pig iron, a high-carbon molten iron. The pig iron, along with scrap steel, is then transferred to a basic oxygen furnace. Here, pure oxygen is blown at high pressure onto the molten metal, reducing its carbon content from about 4% to less than 1%. This oxidation reaction generates intense heat, further melting the mixture and helping remove impurities like silicon, phosphorus, and sulfur, which form slag and are separated from the steel. Another widely used technique is the electric arc furnace (EAF) process, especially for recycling scrap steel. In an EAF, scrap metal is melted using powerful electric arcs between electrodes. The molten steel can be adjusted chemically to meet required specifications by adding alloying elements such as chromium, nickel, or vanadium. Steel manufacturing is a complex industrial process carried out in large enterprises like Trineke Zelezarny, which combines advanced technology with continuous research and development. The process begins with the production of coke from coal, a crucial raw material used in blast furnaces to extract iron from iron ore. Once iron is produced, it is converted into steel through refining processes that remove impurities and adjust the chemical composition to achieve specific properties. Once the steel is refined, it undergoes secondary steel making for precise composition control and removal of remaining impurities. The molten steel is then cast into solid shapes through continuous casting, where it cools into semi-finished forms like slabs, blooms, or billets. Open die forging is a metal shaping process where heated metal is compressed between flat or contoured dies that do not completely enclose the workpiece. It is ideal for producing large, customized parts, ranging from 1 kilogram to 80 tons, with lengths up to 23 meters. The process refines grain structure, improves mechanical properties, and reduces defects. Open die forging is often combined with precision machining, enabling components up to 100 tons to meet tight dimensional tolerances. It's widely used in industries like aerospace, energy, and heavy engineering for shafts, rings, and other large structural parts.